Now let us solve a problem on bending stress or the bending equation. So here the problem is a square beam having cross section 20 mm by 20 mm. It is having the cross section of 20 by 20 square cross section. 20 mm by 20 mm in section and 2 meter long. So B is equal to 20 mm, D is equal to 20 mm, width and depth of the beam 2 meter long, L is equal to 2 meter in terms of millimeter, 2000 millimeter is simply supported at the end. So it is simply supported beam. The beam fails when a point load of 400 Newton is applied at the center of the beam. Load on the beam is given, point load that is 400 Newton. Okay. What UDL per meter length will break a cantilever of the same material 40 mm wide, 60 mm deep and 3 meter long. Here there are, in this problem there are two cases. Okay, the first one is a square beam. Okay, square beam simply supported and it is 2 meter long and 400 Newton is applied on the square beam. Okay, this is the first case. The second case is one more beam, that is cantilever beam, 40 mm wide and 60 mm deep and 3 meter long. Okay, initially we will take the first case. Okay, we'll take the first case, that is square beam with 2 meter long and 20 by 20 cross section, which is applied with 400 Newton at the center. By taking this condition, we will solve for bending stress or the maximum permissible stress F. Okay, knowing the maximum permissible stress F value, we will calculate the UDL per meter length of a cantilever beam with 40 mm width and 60 mm deep and 3 meter long. Okay, now I'll take the case 1. Case 1. Case 1 is calculation of maximum permissible stress F. Okay, for simply supported beam. For that I have written the data below. Correct, I have written the data. Now we'll take the bending equation, that is M by I is equal to F by Y. Okay, for simply supported beam carrying concentrated load at the center, the formula for maximum bending moment, we know that it is WL by 4. Okay, if L is the length of the beam, therefore M is equal to WL by 4. So W is 400 into length 2000 divided by 4. It is 400 into 2000 by 4 means 500. It is 200 into 10 power 3 Newton millimeter. Okay, the moment of inertia of the rectangular section is VD cube by 12, which is 20 into 20 cube by 12. 20 into 20 cube. By 12. It is 13.33 into 10 power 3. 13.33 into 10 power 3 mm raised to 4. Okay, and y is distance of extreme fiber from the neutral axis. Here, if it is a neutral axis, distance of extreme fiber will be 20 by 2, d by 2. Okay, so y is equal to d by 2. 20 by 2, 10 mm. Okay, I can rewrite the equation one as F is equal to m by I into y. Everything is now just substitute 200 into 10 power 3 divided by 13.33 into 10 power 3 into 10. So 200 into 10 power 3 into 10 again. One more 0 divided by answer. Answer is 150. F is equal to 150 Newton per mm square. Okay. Now, using this maximum permissible stress, we will evaluate the UDL per meter length. Okay, UDL per meter length with the cantilever beam of same material. Okay, the material of the beam is same, but in the first case it was simply supported beam. In this case it is dimensions 40 mm wide and 60 mm deep. Therefore, as the material of the beam is same, the permissible stress will be same only for both the cases. Now we will utilize this maximum permissible stress value for solving or for finding UDL per meter length that the cantilever beam can carry. Okay. Now case 2. Case 2. Calculation of uniformly distributed load with permissible bending stress. F is equal to 150.37 Newton per mm square with cantilever condition or cantilever beam. Okay. Now the cross-sectional dimension for the cantilever beam is different. It is given as 40 mm by 60 mm, correct? B is equal to 40 mm, B is equal to 60 mm. Here I'll write it. B is equal to 40 mm, D is equal to 60 mm. Okay. And cantilever of length 3 meter. Length is also different. L is equal to 3 meter, which is 3000 millimeter. Okay. And F value is 150.37 Newton per mm square. Newton per mm square. Okay. Now M by I is equal to F by Y, bending equation. I is equal to BDQ by 12. which is 40 into 60 cube by 12, which gives 40 into 60 cube by 12, 720,000 mm raised to 4. Then y is equal to distance of extreme fiber from the neutral axis, which is d by 2. 60 by 2, 30 mm, and F is known 150.37 Newton per mm square. Therefore, in this case, the moment becomes F is 150.37, or else I'll rewrite the equation. M is equal to F by y into I, which gives F is 150.37 divided by y is 30 into moment of inertia 720,000. Okay, so into 150.37 divided by 30. Answer is 3.6 into 10 power 6. M is equal to 3.6 into 10 power 6 Newton millimeter. Okay. Now we have to find the intensity of the UDL that the cantilever beam can carry. W per meter length. Okay. So L is given as 3000 millimeter length of the cantilever. Okay. So we know the moment M is equal to 3.6 into 10 power 6 for cantilever beam carrying UDL. Okay. The maximum bending moment will be at the support. Okay. Maximum bending moment will take place at the support. It will be WL square by 2. It will be WL square by 2. Means moment of this UDL about the support. W into L by 2, which gives WL square by 2. WL square by 2 is equal to 3.6 into 10 power 6. W is the unknown factor into L, 3000 square by 2 is equal to 3.6 into 10 power 6. So solving this, we'll get the value of intensity of UDL. So here 3.6 into 10 power 6 into 2 divided by 3000 square. 3000 square. Suppose it is 0.8019. It is Newton per millimeter. This is W per millimeter because distance are taken as millimeter. Then in terms of Newton per meter, it will be W is equal to, you can convert this as Newton per meter, 0.8019 Newton. So I am converting millimeter into meter. 1 millimeter is equal to 10 power minus 3 meter. So Newton per meter. It will be 0.8019 into 10 power plus 3 Newton per meter. W is equal to, it will be 0.801 means 801.9 Newton per meter. Okay, or else we can stop the solution to here only. So to this we got the intensity of the UDL that the cantilever beam can carry with the permissible stress of 150.37 Newton per mm square. Okay, so this completes the solution of this particular problem. Okay, in the next video we will solve one more problem. Okay, thank you.